Okay, so this is our intro for Wednesday. So what we have is we have the table, and we have the edge of the table, and then we have a cart. So that's kind of our frictionless mass that's going to move horizontally. At the corner we have a pulley, but in this case the pulley is not massless. So we have to take into account the moment of inertia of the pulley. And one thing too is that the pulley consists of a pulley and a disc. The pulley is really light, so it doesn't contribute to the moment of inertia. It's insignificant. The actual disc is greater than the pulley. So we have that scenario. So what happens is the pulley is smaller, it's connected physically to the disc. So that changes our calculations a little bit from what we did in class. So let's call this M1, which is the mass of the cart, which we can check. We'll call this M2, that's the mass of the hanging mass. And then we have the mass of the disc, and we also have the radius of the pulley. And we're just going to do this all in variables so that when we measure this stuff, we can use the equation. So we end up with three free body diagrams. We've got the cart. So we have a tension T1, M1, and that's it. We have the disc, which consists of the pulley and the disc. Now there's two tensions applied to this. There's T1, which goes horizontally between the pulley and the cart, and there's T2, which goes between the pulley and the hanging mass. So there's this radius of the pulley here. We also have the radius of the disc, which we will use to calculate the moment of inertia for the disc. Okay, and then finally down here we have the hanging mass. So we have the tension pulling up. We have the weight, W2, hanging down. And this has a mass, M2. So those are the three free body diagrams. I'm just going to leave them as such. We've got to define positive directions. So a positive x is going that way. So it's because it's being dragged that way. We're going to have positive x here. We're going to define positive y going up for the hanging mass. And for the pulley, we are going to say counterclockwise is negative, or clockwise is negative, counterclockwise is positive. So you can see this is going to be moving to the left, and this is going to be going down. So we're going to get a clockwise motion, which is going to end up being negative from a sign perspective. Okay, so let's look at object one. We don't really worry about what's happening in the y direction because there's no friction. If this were a block that was being dragged, we'd also have to do the y direction. In our case, we don't have to worry about that. All that tells us is the weight is equal to the normal force. But like I said, so the friction is negligible. So we have some of the forces in the x direction for object one. So that's M1 times A sub x1. And we only have one force here. We have the tension, T1. So that's pretty simple. Now if we had friction, we'd have, subtract the friction force. If it was on an inclined plane, we'd have to take into account the x component of the weight. Anyway, for our case, that's all that happens with that. For the disk, do the sum of the torques, and they're going to be summed around this axis of rotation, which is the axle, and that's going to be equal to the moment of inertia of the disk times alpha of the disk. So that's just like equivalent for mass times acceleration, except we have moment of inertia times angular acceleration. Now, as far as the torques are concerned, instead of using the radius of the disk, we use the radius of the pulley. So we've got tension T1, even though it's moving from left to right, if T1 was acting on it alone, pulling in this direction, then we would have a positive torque. So you're going to have positive T1. So I don't need to put a positive because of the equal sign, but just to emphasize, you got T1, and the torque arm is the radius of the pulley. Then you have T2, which would cause this thing to rotate clockwise, which is negative. So you have negative T2 times, again, the same radius, the radius of the pulley. So that's for the disk. And then we have the hanging mass. Here we have just forces acting in the y direction, because it's just hanging. So it's going to be some of the forces in the y direction for object 2. That's equal to m2 a sub y2. And what do we have? We have T2 pulling up, and we have W2 pulling down. So that's for this one. And then we finally have to relate the linear accelerations of the two, the cart moving from left to right and the mass falling, and the angular acceleration of the disk. So you can see here, this cart moves in the positive x direction. Because these are connected by a string, this positive x is going to give you negative y. So what that means is that ax1 is equal to negative ay2. So positive acceleration for x1 is going to give you negative acceleration for y2. Likewise, you've got a sub x1. The linear acceleration of this is going to be related to the angular acceleration of this. Remember, a is equal to alpha r. In terms of the sign, a positive x gives you a clockwise rotation, which is negative. So that's going to be negative alpha for the disk times the radius for the pulley. Because the pulley is connected to the thread, not the outer diameter. And then you also have, finally, the moment of inertia for the disk is equal to 1/2 the mass of the disk times the radius of the disk squared. Because the pulley has negligible mass, it's the disk that's causing the inertia thing. So all we have to do is put all this stuff together. And the best way to do it is to solve this one for T1, plug it in here, solve this one for T2, plug it into the second equation. So we plug everything. So we already have this one solved for T1, so we can do that. And we can solve this one for T2, so let's do that. So what you'll get is T2 is equal to M2 a sub y2 plus W2. And we'll add a page here and we'll substitute everything in. So let's start. And what we'll do is we'll solve for alpha for the disk, and then we can always do it the other way. once we have alpha for the disk, we can calculate A1, X1, and A2, Y2. Okay, so let's write that here. So we have moment of inertia for the disk, alpha for the disk is equal to T1, but T1 is equal to M1 A sub X1. So that's T1 in here times the radius of the pulley. Okay, then we have minus T2, but T2 is equal to M2A sub Y2 plus W2. So that's T2 plugged in here, you get N times R sub P, R radius of the pulley. Okay, now we'll go to the next page and we'll make these substitutions. So A sub X1 is negative alpha for the disk times the radius for the pulley. So we get moment of inertia of the disk times alpha of the disk is equal to M1. I'm going to go ahead and put these two together. And then you got A1x. A1x is equal to negative alpha for the disk times the radius for the pulley. So that's substituting this to this part right there. Then you have M2 times A sub Y2. So A sub Y2 is negative A sub X1. So instead of negative alpha D, it's just going to be positive alpha for the disk times radius of the pulley. So what I'm doing there is I'm substituting for this. I substituted this. Oops. Okay, and then I've got one more. Then I've got plus W2 times R for the pulley. Okay, let's add a page in here now. So what we're going to do is we're going to solve for alpha for the disk. So to do that, let's just multiply everything out here. So we got I for the disk times alpha for the disk is equal to negative R1 radius of the pulley squared times alpha for the disk. In this term here, we're going to get negative M2. And you get R of the pulley times R of the pulley. So it's R of the pulley squared times alpha for the disk. Just multiply this times that times that times that with the negative sign. Combine the two R for the pulleys to get R for the pulley squared. And then I've got negative W2 times R for the pulley. So now move everything involving alpha sub D to the right-hand side. Notice these will become positive. And then got negative W2 times radius of the pulley. Then you could factor out alpha sub D. It's going to be I for the disk plus M1R for the pulley squared plus M2R for the pulley squared. That equals negative W2 times R for the pulley. And if we divide it out, we'll get alpha for the disk is equal to negative W2 R for the pulley divided by moment of inertia of the disk plus M1 R the pulley squared plus M2 R the pulley squared. So you can see, in class we talked about a different form of this, where we had masses, and then we converted the moment of inertia of the disk into a mass type term by dividing by the radius of the pulley squared. Here, we're getting everything in terms of moment of inertias. So that's how you would calculate, theoretically, the alpha for the disk. Let's go ahead and calculate, let's say, a sub x1. So what would you do? So all you have to do is take this and multiply by negative alpha for the disk, r for the pulley. So you get W2 r the pulley times negative r the pulley. Right? All we're doing is taking, to get a sub x1, we've got a sub x1, we multiply alpha by negative r sub p. So that's how we get a sub x1, and we divide by what we had before here. And what we could do, you see these negatives cancel out. So we just get positive W2. We get r sub p squared. But if we take this and divide by r sub p squared in both the numerator and the denominator, these will cancel out with that, and we won't have any radius of the pulley in the numerator. And what you get in the denominator is I sub d over r the pulley squared plus m1 plus m2. And that is the equation we had in class. And then to find a sub y2, you just change the sign. It's negative, so it's going to be negative W2 divided by moment of inertia of the disk divided by the radius of the pulley squared plus m1 plus m2. So you can see I've got all three of them. So again, this was the one that I came up with in class. Because what's driving this whole thing is the weight. If you didn't have the weight, nothing would happen. Just sit there. But what's contributing to the inertia of the system? Well, we have the inertia of the rotating the disk, and then the inertia of the two masses. This way up here with alpha, you can think of it in terms of a rotating system. When you're dealing with linear acceleration, you kind of think of it as a moving system. So here you've taken the rotating part and kind of rewritten it as a linear part. Here we've taken linear parts and rewritten them more as rotating things. So what we're going to do in class, these are the equations that you'll need for your calculations. What we're going to do is we're going to do two scenarios. One is where we have the disk attached to the pulley, and one where we don't have we take the disk off. So one part will be where the moment of inertia of the disk is 0, and ultimately we'll end up using wherever it is here. We'll be using this equation here, except this term will be 0. This term here will be 0. So that's without the disk. And then we'll put the disk in there. So when you include the disk, this thing should accelerate slower. This is adding to the denominator, which means it's going to reduce the value. We'll try 3 or 4 or 5 different W2s, the same W2 for both scenarios, but we'll have some with the disk attached and some without the disk attached. Now in class today, what we did was we had it where we didn't have the cart. So M1 was equal to 0, and you can see that's how the equation reduced to. Now, if you had M2 equal to 0, then W2 would be equal to 0, and nothing would happen. So I guess one thing we could do, and I didn't do it, but we could replace W2 with M2G. That way we'd have it in terms of masses instead of in terms of weights. So that just takes one step out of the whole calculation. But, it all came down to doing free body diagrams of the three elements that are connected together, and to relate each. So how are they connected? Well, the tension in the cables. Also, T1 does not equal T2. T2 has to be greater than T1 for this thing to actually rotate. When we used to have a massless pulley, these are equal to each other. But if you have a pulley that's attached to some kind of disc that has a moment of inertia, then T1 and T2 are not equal to each other. So that's one way they're related. And secondly, they're related by the fact that as long as this thread is not slipping, then the speed of the thread on the pulley is the same as the linear speed of the thread as it moves through space.